Hello everyone. Today in our video clip I'm gonna talk about section 9.4 of our textbook. It is about something called mathematical induction, and I have to admit this is the most abstract topic for the course, so I'll try to go as simple as possible. I'll try to explain it in the language of Greek calculus algebra at our level. Hopefully you guys can have a sense of it. So basically, math induction is a technique trying to prove something that is true forever. So let me just first give you the idea, the way that the book represents, and then I'll give you examples, and I hope that the examples is going to make more sense to you. So say you want to prove that Pn is true for n. How do you prove the statement of anything, right? P and n is a counting number. Pn is true for n means what? P1 is true, P2 is true, P3 is true, P4 is true, P5 is true. This is any n is true. Okay, so how do you prove it's true for n using math induction? And we're going to follow a couple steps. Step number one, you need to check if P1 is true. Okay, so this is called the initial step, the first step. Right? It's true for any counting number n, start from 1, right? So is it really P1 is true? And number two, you try to prove that if Pk is true, then the next step, which is Pk plus 1, is also true. Okay? And what does it say? So you got like the first statement, P1 is true, right? So the second statement say what? If the present step is true, then the next value will be true as well. So P1 is true, and the second statement true means what? P1 is true, and P2 is also true. Okay? And now what? P2 is true, and according to the second statement right here, then P3 is true. P3 is true, and P4 is true. Therefore, it's true for all the natural number. Okay? So basically, you can prove a statement using a mathematical statement, anything, using a math induction via two steps. First, check if the initial step is true. Okay? And you make an assumption. If this all the way true, all the Pk is true, then Pk plus 1 is true. If any math statement that satisfies the two conditions, then you can say that by mathematical induction, the statement will be true for any natural number n. Okay? And I know this is abstract, so I think it's easier if I'm going to give you an example. All right? So let's start with an example. Okay. Example. Prove that 1 plus 2 plus 3 plus da 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 all the way to n is equal to n times n plus 1 over 2. So basically in this problem they ask you what? You look at the left hand side, it's a sum of the first n natural number 1, 2, 3, 4, 5 all the way to n is equal to n times n plus 1 over 2. So if n equal to 100, that means what? You add 1 plus 2 plus 3 all the way to 100. If n equal to 50, then 1 plus 2 plus 3 all the way to 50. But anyway, whenever you have a sum of the first n numbers, doesn't matter what n is, you add them up, it's always equal to n times n plus 1 over 2. And that's true for any n. So this is really our Pn statement. Okay? So how do we prove that this thing is, by the way, this is really our Pn, the whole statement. Okay? So how do you prove that this equation is always true for all n? So using math induction, we're going to start with first step. We check for P1. What is P1? Let n equal to 1, right? P1 means check for n equal to 1. Check when n equal to 1. What happened when n equal to 1? The left hand side is just a sum of a single term, which is 1, right? 1 plus, that's it. Check equal n equal to 1. So 1. What about the right hand side? Right hand side, so if you look at n equal to 1, you got 1 times 1 plus 1 over 2. Is that really equal to 1? Yes, so it's true. Okay? And technically, you only need to check for P1, for n equal to 1. But just try to convince you that this is true for any n. Let me just check for a couple more values. I can check for n equal to 2, 3, 4, 5, and I claim that the statement Pn right here will be true all the time. Okay? And this is not necessary when you perform a formal proof for this type of problem, but we are in a lecture, so I just try to convince you more. Say, how about n equal to 2? Optional, okay? Try n equal to 2, see what you got. The left-hand side will be the sum of two terms n equal to 2. So 1 plus all the way to 2. 1 plus 2. And on the right-hand side, n equal to 2, you got what? 2 times 2 plus 1 over 2. Are they equal to 3? Both sides? Yes, 1 plus 2 is 3, right? 2 cancel out, 2 plus 1 is 3. Let's check a couple more. Just try to convince you all that this equation, this statement Pn right here, is true for any value n. Okay, check. For n equal to 3. See what you got. Left hand side is 1 plus 2 plus 3, right? N equal to 3 right here. So you start with 1 plus 2 all the way to n, which is 3. And on the right hand side is what? N equal to 3. I got 3 times 3 plus 1 over 2. It's equal to 6, right? 1 plus 2 plus 3 is 6. This is 3 times 4 is 12 divided by 2, 6. You see? It's always true. And it's at least n equal to 3, up to. How about n equal to 4? See what? 1 plus 2 plus 3 plus 4, this is what I got on the left. What about the right hand side? N equal to 4. So we got 4 times 4 plus 1 over 2. 1 plus 2 plus 3, 6 plus 4 is 10, right? So 5 times 4 is 20 divided by 2 is 10. They're all correct. So with that many steps of checking, I start kind of believe that really this formula is true for n equal to 1, n equal to 3, 2, n equal to 3, n equal to 4. And I strongly believe this n is going to be equal to 4. Then n equal to 5 will be true as well. N equal to 6 is still true. But how can I prove that it's true for all values of n without really checking every single one? Because there's no way that I can check every single number. Okay. So the second step for math induction is say, well, okay, the first step is right. I'm going to assume that the equation is true up to n equal to k. And then I need to prove that if it's true for n equal to k, it will be true for n equal to k plus 1. And therefore, it's be true for any value of n. Okay, let's move on. So I'm going to assume that the equation is true for up to for n equal to k. And what do we mean by that? Which means 1 plus 2 plus 3 plus da 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 all the way to k, right? N equal to k. This is actually pk step, right? P1, P2, k, right? The sum of the first k number will be equal to k times k plus 1 over 2. So we assume that this equation is true. Then we need to prove that. We need to show or to prove that the equation is also true for n equal to k plus 1. Right? So we are at the statement, if pk is true, we try to prove that pk plus 1 is also true. And that means we need to prove that we need to show that pk plus 1 means this. 1 plus 2 plus 3 plus da da all the way to k plus 1. Right? N equal to k plus 1 means what? The sum of the first k plus 1 term, 1 plus 2 plus 3 all the way to k plus 1, equal to k plus 1 times, this is n equal to k plus 1, so k plus 1 is k plus 2 over 2. Keep in mind that we don't have it yet. All we have is this. We check that the first step is true, okay? And we assume that the k step is true. And we try to prove that the k plus 1 step is also true. All right? And by the way, this is pk, and this is pk plus 1. Okay? We have pk. We assume pk is true. We try to prove that pk plus 1 is also true. It's right here. So how do we prove pk plus 1 is also true? In other words, how do we prove that the sum from 1 to k plus 1 equal to k plus 1 times k plus 2 over 2? We got to use the assumption that we have right here for pk. We know the sum from 1 to k plus 1 is really the sum of 1 plus 2 plus 3 plus all the way to k, and then plus k plus 1, right? But the sum from 1 to 100 is what? 1 plus 2 plus 3 plus 4 all the way to 99 and plus 100. Okay? The sum from 1 to 50 is what? The sum from 1 to 49 and plus 50. So the sum from 1 to k plus 1 is the sum from 1 to k and plus k plus 1. Why do we need that? Because we know that the sum of the first k term, according to our assumption, is equal to k times k plus 1 over 2. So the first k terms right here will be equal to k times k plus 1 over 2. And then you add k plus 1, which is the last term. And hopefully they'll be equal to whatever you have on the right hand side. So how do you add the two numbers? Make the same denominator, combine the two fractions. So denominator is 2, so I modify the second term is like 2k plus 1 over 2. Now fraction is over 2. I'm going to simplify the numerator and factor out. I got k squared plus k, distribute k. K squared, k times 1 is k, plus 2k plus 2, right? And this is k squared plus 3k plus 2 over 2. I combine the like terms and factor the top out. I got k plus 1 times k plus 2 over 2. So really, the left hand side is equal to the right hand side. And the whole picture is saying what? P1 we check is true, and if pk is true, then for sure pk plus 1 is also true. Alright? And with that, you can safely say what? By math induction, so we're going to write a conclusion right here. Okay? Therefore, by mathematical induction, the equation is going to be true for all natural number n. Okay, there are two parts that I want to mention in this section. That point for first, the conceptual part of math induction. The idea is what? You try to prove the next step is true. How do you prove that? We check. We start with true statement. All right, so it's true for at least the initial step, and then we try to prove it. Okay, it's keep being true. So if next step is true, then what? It's going to be true forever. That's all I'm saying. And the second thing that I want to prove in here, try to bring to you in here is what? The technique of solving problem using math induction. You always follow a couple steps. Number one, you check for n equal to 1, and I claim that's enough. And in this, in there is an example. I try to give you more check-in for n equal to 1, n equal to 2, n equal to 3, n equal to 4. The more I check, to try to convince you that really the equation is going to be true for n or n. But you don't need to do all of those, just n equal to 1. And then the second step is what? You assume that the equation or whatever is going to be true for n equal to k. Okay? You don't have it, but you assume it's true. And then you try to prove if this is true, then the next step pk plus 1 is also true. Alright? So we start P1 is true, and along with the second statement pk true, then pk plus 1 is true. So P1 is true will help you say that P2 is true. P2 is true, help you to say that P3 is true, so forth and so on, for it's true forever. That was the idea. And for the technique of using this, you will always use the result that you have on pk to prove for pk plus 1. You see right here, I assume the pk is true. So 1 plus 2 plus 3 all the way to k equal to k times k plus 1 over 2, right? Then when I prove for pk plus 1, 1 plus 2 plus 3 all the way to k plus 1, I will always use the result that I have for k right here. You really need that. Okay, and hopefully this gives you an idea. Let me just give you one or two more examples. Pretty much the same thing, it's just different question. Hopefully if you have more examples, will help you to get a hang of it. All right. Another example. I'm looking at your exercises. All right. How about this? Sum of odd numbers, 1 plus 3 plus 5 plus ... all the way to 2n minus 1 equal to n squared. You try to prove the sum of the first n odd numbers will be equal to n squared. Is that really true? With this type of problem you want to prove in general, you're going to use math induction. So the first step, check for n equal to 1, which is step P1, right? For n equal to 1. What you got for n equal to 1? Means what? You have the sum of just one odd number, which is 1. Is that equal to 1 squared? Yeah, it's true. Okay, and I claim this. For the initial step, you only need to check for n equal to 1. one more time, and I consider this is a lecture, and I try to convince you that this equation is actually true for any n. Okay, so I'm gonna check for a couple more. Try n equal to 2. See what you got on the left hand side. N equal to 2 here means what? The sum of the first two odd numbers, so n equal to 2. So the last term will be what? 2 times 2 minus 1 is 3. So 1 plus 3. Was that equal to 2 squared? Yes, equal to 4. Say n equal to 3 means what? The sum of the first three odd numbers, n equal to 3. Look here. 2 times 3 is 6 minus 1 is 5, right? So what? 1 plus 3 plus 5, you see? The sum of the first three odd numbers. Was that equal to 3 squared? Yeah, because they all equal to 9. It's all correct. Okay? Try n equal to 4. So 1 plus 3 plus 5 plus 7. Was that equal to 4 squared? Yeah. 9 plus 7, you see? The first three numbers sum is equal to 9, right? Plus 7 is 14. I'm sorry, 16. 16 to 4 squared. Yeah, it's always true, right? Try n equal to 5. 1 plus 3 plus 5 plus 7 plus 9, you see? It's equal to 5 squared, which is 25. Always true. So, I believe that this equation is true for any n. So I'm going to prove it in general. So this is the initial step. I check for the first couple cases for n equal to 1, 2, 3, 4, 5. Next, I assume that the equation keep being true until n equal to k. It is true for